this sizing constraint. You have to make sure access is stronger and cooldown is stronger. So this is actually hard to meet, right? So what people came up with is they introduced 8T SRAM, whose structure is shown here. And the biggest difference in this 8T SRAM is you actually have these two transistors, which is dedicated to read operation. Okay, so this has nothing to do with write operation. This is only for read operation. So you can see that this one of these internal node voltage is connected to this M4, and then you have separate read bit line here, this bit line, and then you have separate read word line. So what this do is, if you store 1 here, and if you enable this read word line, which means you turn on this M3, you can discharge this read bit line through this transistor stack if you store 1 here. But if you store 0, then your read bit line will not be discharged. So this is single-ended reading. You only have 1 bit line. You're not reading with differential sensing. But this still works very well because internal node is only connected to gate of transistor, which means there's no read offset. Originally we had read offset because we were reading through this bit line, and this internal voltage is somehow connected to this bit line, right? But in this case, we don't have to worry about this read offset. So what that means is, when you have transistor sizing issue, so originally we had this PMOS, NMOS, and we had to make sure this happens. Now we don't have to worry about this condition. You just need to make sure this is applied. You don't have to worry about pull down PMOS, NMOS is much stronger than access transistor, which was due to the read up, which was for preventing read offset. Right? So for that reason, you have more flexibility on sizing these transistors at the cost of having 2 more transistors. But this significantly improves your stability, because now the transistor sizing on main part, the back-to-back inverter, can be optimized for write operation. And read operation is always stable. So this is actually the SRAM which is used for cache memories in your desktops, especially for the level 1 and level 2 cache. Okay? And this is also good for having separate read and write port, right? You have separate read line, read bit line, and write bit line, read word line, write word line. So you can have one read operation and one write operation going on simultaneously. Alright, so yeah, this is a graph for read operation. So for X60 SRAM read operation, your VTC changes like this. So your VTC margin was like this. But for AT SRAM, you are not using these 2 transistors, so no current is injected to these nodes. So your VTC is just like the original static noise margin for hold case. So that's much safer. Alright, so that was AT-SRAM and memory reliability and yield. Okay, so as technology scales, now we can make larger memory, like more bits per chip, but that means you are scaling, and scaling means you are reducing all the geometries as you make larger chip. So like each transistor is smaller, each storage cap is smaller, each like poly, wire, everything gets smaller. So what that means is your bit line capacitance is also reducing, and the charge you store on the cell, like for DRAM case, for example, that's also decreasing. and the capacitance is also decreasing. And at the same time, you also usually decrease your VDD as you scale, right? You want to use lower voltage for lower power. So your VDD also scales. Everything gets smaller. And at the same time, because your charge and capacitance is getting smaller, you actually want to use more accurate, like readout circuit, right? You want to be able to detect smaller voltage difference, right? So that's like sensing voltage. How much voltage difference you can sense. So everything gets more accurate. That way you can get smaller. You can use smaller amount of charges for changing the bit line voltage, right? So this actually means you are actually more prone to noise now, right? So your feature size is reducing, but amount of noise, like the charge injected to your system due to some kind of noise, doesn't really change because that's due to like physical environment. Like for example, you have some kind of some particle bombarded to your chip, which will be explained in next slide. Basically, you are more sensitive to noise, and this is actually a big problem. So for example, we can think of many different noise sources in 1TD RAM. So that could be like couplings, like you switch your bit line, your word line, that could give you some noise injected to the surrounding circuit. And you also have leakages, so that could be also treated as noise. But one of the interesting noise you might want to know would be like alpha particle strike. So, you know, the alpha particle is, was it hydrogen or helium? Is it helium?
Helium.
Helium. Okay, helium nuclei, right? Yeah. So these are everywhere, right? Like this is from like cosmic rays and some isotopes. 방사능 붕괴. I forgot the word. So it self destroys, and then you get small particles getting out, like uranium, like those kind of stuff. Radioactive, yeah. So you get these materials everywhere, and like for old days, people often used the lead for the packaging, and which is radioactive. So you actually get these kind of particles coming from like surrounding environment, and that could actually hit the silicon substrate. Then the problem is because of this kinetic energy, you actually generate electron-hole pair on the silicon. So it generates some kind of charge on certain point. So this could be energy. This could be the noise for the DRAM and SRAMs. So now the problem is, in old days, amount of, or the capacitance per cell was large. So even if like fixed amount of charge is generated due to this particle strike, you could tolerate it. But these days, as you can see from this graph, your capacitance is much smaller. Amount of charge you store on your storage cap is much smaller. So that means with the same particle strike, you'll have much bigger impact, right? You have basically your cap is smaller, so you can easily flip the stored value. So this is actually a real problem, and like not only the alpha particle, but like also like cosmic rays that could even matter. So like for example, I heard that data centers have like many server farms and they have like memories on it, right? And somebody realized data center in Denver, in the Rocky Mountain area in United States, they had more errors compared to the data centers located in lower area like on the East Coast or West Coast, and they were investigating why are they having these soft errors, and they actually found that because Denver is located at the very high altitude, they are exposed to more cosmic rays, which actually created errors on these memories. So that's actually a real problem. So even in the servers like you guys use everywhere, like here, they should have some kind of error correction capability because of this issue. Like for your personal computer or laptop, if something goes wrong, you can just turn it off, reboot, go. That's fine, right? But for like like web services or for other type of services that should be always on, like very important service, you should be able to tolerate